dear Chairman, dear honorary members of the conference, ECF 24, dear participants from around the world. It's my great pleasure to give this invited talk here at the conference, to open the conference on multiscale modeling from atoms to components. And I would like to just show you my view on multiscale modeling and hope you benefit a little bit from it, at least from one or the other aspect. Before I start, I would like to thank my co-workers, my dear students, my postdocs, and especially funding from the German Research Foundation and from a number of companies which supported us throughout the work. During this talk, I would like to first introduce you into the topics of length scales and nomenclatures, motivate and give some historical aspects before I enter really multiscale materials modeling aspects. Modeling methods are really important here to mention because we have different length scales and time scales involved. Finally, we go to optimization and development of improved and new materials. And if time allows, we will also talk a little bit about fatigue simulation and at least one new development. I'll start with length scales and definitions. The length scales involved range from nanoscale up to macroscale, with microscales, and intermediate dislocation relevant mesoscale 1 and mesoscale 2 for continuum mechanical aspects. Involved are a number of methods which I will show in a moment. And when we talk about multiscaling, we mean minimum 3 scales are involved, and including nanoscale. If we have continuum mechanical multiscaling, we talk about many scaling to discriminate from real multiscaling. Okay, so why do we do multiscaling? Why are we after these different length scales? Well, when we have a production to make some material for any application we have in mind, we produce microstructures, all these aspects involved, and we are after certain properties which we need for the different applications. While in the past, characterization and experiments are in the foreground to fill this gap, modeling is coming more and more in the last decades. And therefore, I would like to motivate you with the historical development a little bit in this field. And bring out that computational materials engineering helps us to customize materials from production over microstructural property relationship to the application which is needed. So in the past, people looked on different aspects on the microscale, using homogenization techniques for non-local and local modeling for fracture, with one model on one scale and one method. Further on, one model was kept, but several scales and methods were involved. Here, for instance, for metal matrix composites or the finite element atomistic modeling. And later on, and this is what we are talking today, on hierarchical modeling, where several models and several scales and methods are involved, mainly with parametric coupling or multiscale materials modeling. We will go into some of the examples here. So let's go directly into multiscale materials modeling. I would like to start with this slide because finite elements and atomistics have to be brought together somehow. In 35 years ago, when we started with this, about 5 groups worldwide were working in this area. And here you can see that the atomistic field inside the finite element continuum field allowed to bridge the scales at least from nanoscale up to micro, meso, and even macro scale. A crack which was continuum mechanically close to an interface here between a ceramic and a metal is predicted to deviate from its straight path parallel to the interface. But if you look on it on the atomistic scale, due to the lattice constraint, the crack frequently remains on this straight path. Therefore, there is already some benefit from this atomistic view, which we introduced here on this coupling technique, taking temperature already at that time into account, and also waves which could propagate through the boundary between atoms and continuum. Now, fracture is one of the most important topics in our research because we want to prevent it. Therefore, if we take care in modeling on it, we have a better chance to prevent it. And here you see that the scale bridging means that we need parameters from one scale handed over to the next one in order to do simulations based on atomistic properties like work of adhesion or cohesive strength, leading then on the microscale to the stress-strain behavior there with the respective microstructure, sometimes an mesostructure, and finally the fracture energy for the macroscopic behavior.
Thank you.
If you talk with material scientists and materials engineers, you get sometimes different answers for the same question. Materials engineers, they usually have a top-down approach, meaning they go as deep into the microstructure as is needed to understand problems, while material scientists, like I am, we like the bottom-up approach very much, and sometimes go even down to the electronic structure and go upwards scale by scale in order to fully understand on a physical basis without any assumptions or any empirical modelings. Now, the methods are therefore now in the foreground because you need them to understand on each scale what is going on and how the phenomena can be followed. Yeah, here should be a movie running. Here, a dislocation interaction with the aluminum copper interface of a copper Guinea Preston zone is shown. After the cutting by the dislocation, the precipitate is somehow cut by one atomic layer. And what you can see on the shear stress strain diagram is the pale stress, which is referring to the individual planes which are affected. But then when the particle is in the way of the dislocation, we have a strong increase of the shear stress up to the critical resolved shear stress, usually abbreviated with CRSS, coming down then when it's cut and then continuing in the lattice. Okay, it's now understand. It's running. When I press again, you can see this process. The dislocation is moving to the right. Our upper part of the model comes then back to this side, and you can see now the cutting process. The dislocation is hindered by this copper precipitate in aluminum. We increase the shear stress up to this point when the dislocation can move through and is passing through the particle sitting the upper and the lower part by one atomic distance. Molecular dynamics can be used for many different purposes. Here, for instance, you can simulate the film growth process of silicon carbide and silicon. And if you have good or bad parameter sets, you can either find a perfect lattice or a disordered lattice. And therefore, the method can help a lot in discriminate the individual parameters which are needed to do the right simulation and finally production. In this example, you see an aluminum copper alloy under tensile testing conditions. The polycrystal can be easily seen by this high energy grain boundary areas. And when we look inside the material, we have here used a technique where the grain boundaries are easily seen here. Go back for a moment to show the movie. It's stopping somehow, unfortunately. Anyway, what we would have seen is at the interfaces, at the grain boundary, dislocations are emitted nearly at the same time at a certain loading stage. Concrete sources are active with the stacking faults, these planes here in color, and the different colors are just to discriminate between the individual grains. Therefore, molecular dynamics can nowadays be used to simulate strengthening effects, which is one of the most important aspects in material science, to improve materials, whether it is dislocation hardening, we already seen Frank resources, solid solution hardening, but also precipitation strengthening, ore strengthening, grain boundary and phase boundary hardening. And this makes it very valuable in order to predict material behavior. Even individual aspects like cutting of particles in a manifold manner with screw dislocations or edge dislocations is possible in order to better understand what we see in the experiment, for instance, under the electron microscope. Now, one of the examples which struck me most in the beginning, more than 20 years ago, when we did that, we simulated solid solution hardening. Here you can see the individual atoms in black, or a field of atoms, the dislocation line from an edge dislocation moving through and the external shear stress. And a direct comparison with experiments on model alloys of alpha iron with copper or with nickel shows extremely good agreement between the strengthening levels for low concentrations of these added atoms. Here you see the experiments from model experiments with individual atoms contributing, and what is clear, carbon, nitrogen, phosphor, which are sitting in between the lattice positions, have a very high strength increase probability. And this is also found here. We can see here that for a factor of 10 lower carbon concentration as compared to here copper or nickel, we even get a 10-fold higher strength increase. That means in total factor of 100 higher strength. And this is the secret of steel, of course. Now with such a meaning meant, and you can also now play around, do parametric studies. You can analyze if a material with a smaller or a higher shear modulus introduced in the iron matrix produces higher or even better critical stresses than the other material. Or we can see if a material with a higher or smaller lattice parameter has stronger or weaker increase in this critical stress, also compared to this shear modulus effect. One of the first questions you always get when you do molecular dynamics is about the time scale, because usually you deal with nanoseconds, femtoseconds, or picoseconds regimes. And here we got some help from Peter Wolf and colleagues who did MD simulations and compared with experiments and showed that there is a clear continuing prediction possibility from the simulations of experiments to higher velocities of dislocations. And that was used then for polymers to extend the strain rate extrapolated for energy densities in these polymers, and also for stress strain curves in metallic alloys. By changing the strain rate helps us to understand for simulated strain rates which are possible with molecular dynamics, even the stress strain behavior under real laboratory conditions. Similar results have been found with DD simulations. So this is what we do nowadays in order to overcome this time constraint in molecular dynamic simulations. Let me now show you the first, to my knowledge, successful multi-scale example. It is based on a number of projects which have been funded from a German research society with respect to atomic power plants and safety analysis, where copper precipitates were forming during the service conditions, 340 degrees centigrade over 10, 20, 30 years lifetime and more. And the usual way is to do experiments on the microscope, to do tensile tests and see what aging means, namely strength increase due to increased population of copper precipitates. Then, of course, we do fracture mechanical tests and damage mechanical analysis in order to derive J integral versus crack elongation curves. And these increased stress strain curves lead to decrease in these J integral values. Now, this is a well-developed experimental approach. And the idea was, in this series of projects with more than 10 million euro in total involved and experiments running over more than 10 years, to simulate now with Monte Carlo methods the precipitation behavior. Here you see the copper precipitates, how they form. With phase field modeling, we can handle the larger precipitates, and then the interaction of a dislocation with such precipitates of individual size was done in order to get some energies which are needed for dislocation dynamics at the interface between larger and smaller particles, interacting with running dislocations in the material under deformation analysis, and coming out with stress strain behavior with particle arrangements of different sizes, and then following this way to derive J integral values. And by that, you can, of course, also simulate worst case scenarios and come to the situations where the J integral has its lowest value. Now, how can we use this to optimize materials? We can now play in the computer with different compositions of copper. We can increase the strength of the material by certain precipitation situations and look on the J integral. Of course, we always compared with available experiments for different aging states and found good comparison. And by that, we were pretty sure that the predictions are also reliable. If you look on damage mechanical specimens with differently sharp notch specimens, then you can see that the comparison with experiment and simulation looks quite good. Also, the CT specimen is working quite well in comparison. If you have the parameters in hand, that is the initial void volume fraction, particles which develop voids like manganese sulfides or alumina particles, the distance between the particles from the experiment, here parameters sigma k and d, which are either depending on the material or fixed, and then a critical void volume fraction. I come back to that in a minute. Now let me come to one point, because hydrogen is nowadays in everybody's mouth, because hydrogen technology will be something more and more important for our future. Here we have put one hydrogen atom into a model, atomistic model with iron, and have applied external tensile loading. And you can immediately see, in comparison to the case with the vacancy, how strong the strength is decreased, and even more how strong the ductility and deformability is reduced. So hydrogen is playing a role in the decohesion business here around it, and also in changing the plastic deformability there. Now, this deformation in the atomistic regime leads to traction separation laws, which have this shape in the middle and can then be used to simulate the crack propagation in, as you can see, very correct manner in the macroscopic length scale. So multiscaling for hydrogen embrittlement is nowadays very important, and you can change the concentration of hydrogen here. You can change the microstructure in many aspects which you wish. And the comparison really shows how strong the hydrogen embrittlement can really act for one and the same material, always in good agreement with the experiment and the available damage mechanical parameters in the Rousselier model in our case. Now let me come to a number of continuum mechanical aspects in the regime of multiscaling. Here, for instance, we have the results from our dear colleague Thilo Morgeneyer, who should be here for the microscopy or laminography, where you have for differently notched materials, the fracture occurring either at the notch tip or inside the specimen. And in order to describe this void formation in crack propagation, we, based on the modified damage parameter by Rice and Tracy, have analyzed for different materials these parameters A and B, which are necessary to understand these materials. Now, if you apply in a numerical specimen, a cylindrical test specimen with a spherical hole, the stress strain analysis, we find that for different stress reaxiality, which is the ratio of loading in axial and perpendicular directions expressed in this eta value, covering all possible stress reaxialities, that critical void volume fraction of about 5% plus minus was found. Also, when we look on the void volume fraction development as a function of plastic strain, where the void volume fraction is shooting up. And this is really a value which is used also in the typical damage mechanical models like the Rice and Tracy model. Now coming back to the atomic scale and showing then how this is connected, you can see here again this precipitation for a process with Monte Carlo simulations, copper and iron on the left-hand side, or a copper zinc magnesium alloy, precipitation in aluminum alloys. And what is nice here, you can see that still atoms are remaining dissolved in the matrix, besides the precipitation formation in both cases. And you can see different species of the precipitates, red ones and colored ones, which can be discriminated and analyzed in detail. So here, for instance, for different time aspects, we analyzed these magnesium zinc clusters, just to give an example. Now for the iron copper, we did a number of thermal simulations, namely high temperature and then decreasing to low temperature. And you can see here at high temperature, the speed of the change of the positions of the atoms is very high. And then at lower temperatures, of course, it's much lower. What is nice from these calculations is to get the average radius of the precipitates as a function of time, which plays a role in the Lifshitz-Liousoff-Wagner theory, with which you then can describe easily the precipitation process just with a simple formula, not only for copper, but also for highly alloyed steels. If you look on the precipitates themselves, here we did that for 12 precipitates. They look pretty similar, independent on their size. There's a core of copper in red, and blue and yellow are manganese and nickel elements, which are also found in experiments. Closer look shows how the elements are distributed across the cross-section, also in the experiments. Now, nicely, you can change the temperature in these simulations and can simulate different time scales from a few days to hundreds of years or some hours with 10 to the 10 Monte Carlo steps. That means high computation time is here required. And you can follow the composition of the precipitates for each temperature from 300 to 420 with the different equilibrium concentration of copper, nickel, and manganese in this situation, maybe even better seen in this plot, where copper concentration is increasing, manganese and nickel is decreasing as a function of temperature in the equilibrium situation. And what we need to understand the strengthening of these alloys is, of course, mainly the mean radius of the precipitates, because this is something which is strongly determining, among other factors, the strength of the material. Now, when we produced model alloys of iron, copper, and nickel of different compositions, as are depicted here, we can simulate their precipitation situations and the dissolved atoms in it for certain temperatures, and for these compositions, the number of the particles in the simulation box and the size of these precipitates, which change from situation to situation. What is really interesting and what experimentalists evaluated very high is that if you add manganese or nickel, you get a higher number of precipitates, especially in the beginning of the annealing. Later on, this decays a little bit, but this explains that additional elements can really help to get more precipitates which are sometimes required for strengthening reasons. Furthermore, we looked on residual stresses because this was a project together with partners from the Fraunhofer Institute in Saarbrücken. We looked on residual stresses after the Monte Carlo simulation. Here you can use molecular dynamics in order to look around the precipitates, and we see high residual stresses very closely around them. Stresses have been defined as in continuum mechanics, even hormesis stresses as here have been used. And if you plot the stresses along such lines or lines close to this line too, you can see that there are high peaks of stresses around the precipitates. Even we can discriminate perfect lattices and vacancies and see the individual situations. The stresses are very high and are equilibrated by the surrounding. Therefore, no damage must be correlated with such local residual stresses. The residual stresses can be even discriminated between coherency-induced and thermally induced residual stresses. I will not go too much into detail here, but this was a question from our partners. And what you see is that copper is usually in these simulations in tension, while iron matrix atoms are in compression, independent whether you go to longer times, to lower temperatures in the simulation. Except when you add additional atoms like here nickel, then nickel comes into compression, while iron and copper is then in tension, also again for the different situations modeled here. In the end, a comparison between our simulations and the experiments here on the left and on the right-hand side for different nickel concentrations in the copper alloy showed pretty good agreement in the level of the stresses between 20 and 40 or 50 megapascal. If you ask for the experiments, they use Barkhausen noise peak shift analysis in order to get these nice experimental results here. Now, besides such really directly interesting aspects, we sometimes are lucky to find additional information from such simulations here for molecular dynamics. Namely, in that case, we see this special structure of a precipitate from MD simulations of the copper precipitate in very good agreement with experiments. We found the experiment only later after the simulation was done by David Molnar in our group, and therefore you can see and study this even in the computer aside the experiment. Another aspect which was of special interest for our experimentalists was the part of Ostwald ripening, because there's always debates, when does it start, when is the growth process finished? And here we looked on two situations with 1 or 10 atomic percent copper. And let us concentrate here on this last slide, where you see the particle density as a function of time for both cases. And you see that for the 10 atomic percent copper, the red curve, the growth phase is earlier finished than for the 1 atom percent copper alloy. And you can easily see by these 3 phases, A, B, and C, colored in different colors, when the nucleation, when the growth, and when the coarsening or Ostwald ripening phase is there. Now with both methods, Monte Carlo simulations and molecular dynamics, and in addition ab initio calculations on the atomic scale with electronic structures, we got the task from a copper company, and I'm allowed to speak about that because it's published already, what alloying elements should be used in order to improve their alloy arsenal, which they already have, in order to be ahead of, let's say, experimentalists which have enough manpower to do hundreds and thousands of experiments with different alloys. So the atomistic view gives us the local surrounding of the atoms. Monte Carlo gives us this number precipitates with respective time, and the dissolved nickel, for instance, here with a time helps us to understand the electrical conductivity. The task was to look on silver, iron, magnesium, chromium, besides silicon and nickel, and we found the respective precipitates, put them in the molecular dynamics simulation, and could discriminate the strength increases by the different alloying elements. And this helped the company to get new alloys with 2 of these elements, which we looked on, and get hopefully good competition with their partners. Now, fully different picture for continuum mechanical problem here for a doublet steel or dual phase steel, where we have around this blue martensite phase, the green austenite and ferrite phase, and in between we have geometrical necessary dislocations, which were found from our partners in Düsseldorf and shown here in this plot. We have put them in this green colored area between the martensite and the matrix phase. And when you have 3 phases like that, you can even do analysis for different sizes of these martensite plates. And independent whether you use 10 or 2 areas where you introduce these geometrical necessary dislocations, which increase the strength, you always get the correct value if you take into account both aspects. There was no other way to find this result. This was a task given by Thyssen to a number of institutes. You have to take the dislocations here into account. Voids is another aspect which is very important to analyze, especially for our artificially manufactured materials. This can be done and discriminated for different void volume fractions, for different alloys. We looked on the crack propagation here, and always with voids, we see some worse situation after, especially after the peak here for an aluminum silicon magnesium alloy. In ceramics, there's a nice procedure to calculate toughness and strength from these bending tests. Here we use 2 different void situations, and you can see strong differences. Of course, larger voids are more detrimental, especially here in ceramics, than the smaller voids. Crack propagation, as I mentioned earlier, is in the focus of many of our analyses. The comparison with the experiment with this damage parameter shown earlier shows very good agreement in the microstructure, inside the microstructure. Here we polished away surface material, and we can use it to understand how additional phases here shown in blue influence this crack propagation behavior. Besides these metal matrix composites, we are working on fiber reinforced composites because they became more and more important in the recent years. And if you look here on the polymer matrix material with some, I hope it's working in this movie, yeah, with some montmorillonite inclusions in this shape. We have here some organic modifier, which helps to improve the interface. And here you can see how the polymer adheres to this organic modifier. The traction separation law from atomistic simulations is used in representative volume elements in order to simulate a tensile specimen for 2 grades. And the good agreement in the stress-strain appearance is obviously seen also here for this polymer composite. So in all cases, we look on simulation methods on all length scales, but also on experiments in a similar way on all length scales in order to compare with and to be sure that everything is well captured. Now let me come to the second aspects in this presentation. And I'm not sure how much time I have. But in the multiscale modeling, which leads sometimes to cracking here. We want to come from the atoms to the component. And the most important aspect here is the short cracks, because they dominate 80 or 90% of lifetime, while long cracks are very well captured by finite element procedures with typical toughness analysis. The critical resolved shear stress is also here, the relevant value. We did molecular dynamic simulations in order to look on dislocation developments and the appearance of the first permanent dislocations. And from the analysis, we can derive the critical resolved shear stress here for this method. Experimental methods use this micropillar test in a nice manner. It's a cooperation with people from Slovakia, shown here below. And they give also very reliable critical resolved shear stress values for our analysis. So this I've shown before. The J integral values we got from Rousselier analysis, and from them we can derive critical crack initiation energies, JIC or JI, and they are also one input parameter for this Nakamura model, which we use for taking care of the small crack development. And if we can handle the small crack development here in the microstructure crack initiation phase, we have the number of cycles for the crack initiation phase. The Nakamura model is attractive because it is physically based. It is fully developed, this formula where this JI or WC value, but also the grain size and elastic parameters mu and nu are involved. The shear stress on each slip lane is calculated with finite elements, and the critical resolved shear stress is here a relevant parameter. Here we use the small model in order to analyze surface roughness and the influence of the stress level, which is pretty high. The influence of grain shape and orientation can also be seen for different grain sets to be extremely high. That is why we have such a high scatter in fatigue tests. And the influence of Young's modulus can be captured. Also the influence of the critical resolved shear stress, which is shown here for nearly 10% difference of critical resolved shear stress in the model. And finally, this crack initiation energy is also varied by about 10% and is shown to have some influence as well. Now, hydrogen again is known for its strong decrease function in the J values, and this is basically due in the fatigue regime, at least from the lower WC value. Now, the propagation, as I mentioned before, we capture with the Paris law, and then in the end, the final number of cycles takes into account the initiation and the propagation phase, and if everything works well, we have at the end 1 point in the Wöhler diagram in the SM curve, and we do that for every stress level to get the full diagram. That can be applied to components, like here a component from Bosch, a pump, also published, therefore I can show it. Here's the micromechanical model for Nakamura analysis. We have obtained from the company the Wöhler diagram for the material, and you know from short cracks that there's a decay in the crack propagation rate and then an increase, and this is exactly what we can follow in this analysis with the Nakamura model. For different loading levels, we see then cracks coming up in the microstructure in the critical notched regime, 150, 300 Newton, more cracks appearing, 450, even more cracks for different microstructures, similar crack situation, decaying of the crack propagation rate, and then going to the macroscopic crack, which is then finally leading to failure. And as I mentioned before, this gives us 1 point in the component Wöhler diagram in the end, with the discrimination of the number of failure for the initiation and propagation phase. And if you compare in the end the initiation, these are the red crosses, and the final failure, which are the squares, there's not much difference, but the blue line is simulation, and the black one is the experiment. In very good agreement are the both. The endurance limit is in reasonable good agreement without any adjustment, without any empirical modeling, just from scratch. Now, what we teach is that BCC materials and FCC materials have different Wöhler diagrams. This is basically true, but in principle behind is that the critical resolved shear stress is responsible for the height. This is shown here for a number of different materials with FCC and BCC structure and different critical resolved shear stresses. This has been published, and therefore, when we plot the endurance limit as a function of tensile strength, we get some scatter. But if we plot it versus critical resolved shear stress, we got exactly dependency on that. And therefore, machine learning can be used in future to better select materials based on this criterion rather than on the strength of the material. Now, finally, we need the parameters for Paris law. And you may say, well, this you have to get from experiments. And I have to answer no. You can also get the C&M parameters by putting the micromechanical model at the tip of the differently long crack and calculate then the Paris parameters for each situation. And what we find is then similar as an experiment, C&M parameters for the Paris law, just from scratch, just from physics. And therefore, we have now basically all the parameters influencing our SN diagrams in hand. At the moment, we are working on the last step, inclusions. Voids, I can show you some points in a minute. And that helps to improve materials, even under fatigue loading. We have done a porosity analysis study from a wind turbine from Schaeffler, where voids have been found underneath the surface. Partners have done the experiments in Aachen. The parameters for the Tanaka-Mura model are very well known or given in literature. Here is the modeling approach of the component with the microstructure. And if you introduce a few pores, you can do some modeling studies. The upper row is without, the lower row with these black voids. And we see basically no big difference just by looking with the naked eye on it. But if we study the crack propagation, we can see that the voids strongly influence the individual cracks which emanate. This can even be better seen in this last slide here, where the voided material is the upper one, the purple one, and the blue one is the unvoided material, which has much longer endurance times. We have summarized some of these studies in this newly appeared book on fatigue. And here are the conclusions. Multiscale means multiscale in the length scales, especially using many methods, deriving many material science aspects, and we can improve materials, and we can even develop new materials. We are now in the moment going in the different aspects of selective laser melting and artificially manufactured materials, simulate the microstructures which evolve, and then apply multiscale materials aspects as shown before. Just part of it is published here in this new book with Javad Katkodabur and Felix Dayadi, and the multiscale materials modeling and micromechanical aspects are published here in these two books. And with that, I would like to thank you very much for your attendance and for listening. Thank you.